Let's talk a bit about the convexity, because if you remember, that's going to be one of the topics. It defines actually some kind of a shape. Sorry, so I was already showing the next thing. Convexity is something that is some property that we can define for both a set or for a function. Okay, so we will talk about the convexity of a set or the convexity of a function. So let's begin with a set. A set is convex if the segment joining any two of its elements is entirely contained in A. Okay, so here you've got a convex set, you've got one point, another one, and you go from one to the other. The segment going from one to the other is entirely contained in your set. Whereas in that one, you've got one point, the second one, and the segment is not entirely contained in that set. Okay, there is one part, that's one, no, that does not belong to the set. Okay, so one way, so this is a visual ID, but one way to describe it, how do you make a segment out of 2 points? So you've got one point x1, another point x2. It could be in R, it could be in R2, it could be in anything. So maybe you've got x1 that contains x1x, x1y, x1z, and same thing for x2. You can really make the segment by considering all the points in between the two by saying I take a real t between 0 and 1 strictly, and I create the linear combination tx plus 1 minus tx2. So of course, as it's a linear combination, it's still something that belongs to your space. So if ever x1 or x2 are items in R3 or in R20, that is still something that belongs to the same space. So it's t. So this is it. So all the points of the segment are going to be described by all these points for t varying from 0 to 1. When t is equal to 0, you are describing point x2. When t is equal to 1, we are describing point x1. And so all those in between are going to be these ones. Okay, so we've got a convex set if all the points that are described here belong to the same set A. All right? And actually, we're going to describe convex functions. So that's next slide. Convex function, the idea is that if you look at the graph of your function, so that's one intuitive idea in R for functions from R to R, the graph of your function, and you look at the points above your graph of your function, it creates a convex set. Okay, so for instance, what would be not convex? Something like this, or something like that. If you look at the set of points above this graph, what should be above this graph, of course, this is not a convex set, because if I take 1 point here and 1 point here, that goes outside of it. Okay, and that was convex, but this would not be convex, all right, because above is not making a convex set, right? Okay, so that's one way of describing it. Another way of describing a convex function is, which is absolutely equivalent, is if the line segment between 2 points of the graph of the function does not lie below the graph between the 2 points. So that's equivalent to what we said. Okay, if I take the line segment, it's above the line of your function. Another way that you may see it described is if you take any of your tangent line, locally, the graph of your function is above your tangent line. That's another way you will see it described. And in any case, one way to say that, we've got a similar description that is going to work for any real function for any number of variables. Same idea. The image of the segment points are smaller than the segment that you can make between the image of the points. Okay, so that's what we have done here. You take something that belongs between x1 and x2, so you take one item in the segment, so tx1 plus 1 minus tx2, take the image of that by the function, so that's this point. It's below the segment that you make between the tf of x1 and 1 minus tf of x2. It's below this one. Okay, so that's for convexity. Why is that important? Well, we will see that later. That's helping us characterize the nature of some candidates for optimum. But what we can directly have is that when we want to minimize a function and you are looking at a function f that itself is strictly convex on a set that is convex. So strictly convex is just that the inequality previous is a strict inequality. Okay, so the image is strictly below the segment line between the images of your points. Then there exists at most one solution to the minimization problem. Okay, so one easy proof of that, we can go over that quickly. If we've got two minima, okay, x1 and x2, at x1 star and x2 star, so you've got f of x1 star is equal to f of x2 star is equal to some minimum value, then using the convexity, we can make well, the middle point in between those two. So if it's a convex set, if A is a convex set, then this middle point belongs to A again. And then what we will have is that the image by F of this point, because of the strict convexity of A, should be strictly below 1/2, so that's t equal to 1/2. 1/2, well, the middle value between f of x1 and f of x2, which of course is they are both equal to m. The average is going to be m, and so we get that f of x star is strictly smaller than m, which contradicts the fact that m was a minimum value.